Hello, welcome back to a new video. In this video, we're going to talk about hyperconnections. So in the last video, we talked about how we do the parallel embedding, how we initially create the hyperconnections. And in this video, we're going to dive into these transformer blocks and in particular see how the hyperconnections flow into them. So if we look at self.layers, we can see here that self.layers is just going to be a list of blocks. And if we look at where block is defined, we can see that the forward of the block looks very similar to traditional transformer where you have your attention and your feed-forward network. But before going into these, we always call self.hc pre, and we call it self.hc post. And you can kind of think of this almost like a form of compression and decompression, where we're going to take our hyperconnections, we're going to go HC pre, and that's going to kind of merge them together into a single hidden state. That's going to flow through the attention. Then we're going to bring it back out into our hyperconnections. And then when we do the FFN, we're going to do it again. So we're going to come back into this merged hidden state. We're going to go through FFN, and then we're going to come back out. So conceptually, it's very similar to ResNets, where, typically in ResNets, you'll have this residual connection. And the basic intuition is that if you have a really deep neural network, you might not actually need all of the computation in the future. And so what this residual connection is doing is when you're training, it's learning basically when you should do more transformation and when you're kind of done, you can just kind of use your residual connection. And the basic idea is, when you're training, you do the forward pass, and in the back prop, you'll learn when to use the residual connection and when to go through the transformer. Now, hyperconnections just extend this further by instead of having one residual connection, you have four, and instead of a simple add, you have a weighted add. And the basic intuition is that imagine you're a salesperson and you have various personalities. You might be funny, you might be serious, you might be smart, you might be obnoxious. But when you go into a particular sales call, you kind of have to decide. And so the basic idea is that this compression phase where you're basically deciding, okay, how much should I be funny? How much should I be serious? So in this case, I have 0.5, 0.1, 0.2, 0.2, and you combine it into a single person, and you do your sales call. The sales call is either attention or FFN. And then once you're done, you have some learnings, maybe you didn't do well, maybe you did well, and you kind of propagate your learnings back out to these personalities. It's not a complete analogy, but it's almost there. Now, in addition to kind of this decompression phase, this hyperconnection also has this idea of combining the residual streams. So this obnoxious thing is going to learn a little bit from your sales call, but it's also going to take your original obnoxious, maybe at 0.9, but then it might actually also take some from the other residual stream. So maybe 0.033 from smart, 0.033 from serious, 0.033 from funny. And it's not just going to happen for this, it's also going to happen for these as well. I just didn't want to draw the arrows. Okay, so now let's look at the code and build the intuition. So for HC pre, what happens? We're going to first save the shape and D type because we're going to round up to FP32 for stable routing. We're going to then do a norm. And then this is the interesting part where we're going to do this linear layer, and then we're going to do the sync-horn custom op. Maybe in a future video, we can kind of really dive into it. But basically, after all of this, we will get this output that is B by S by 24. And this corresponds with pre, post, and comb. So the pre represents basically this weight, which is how much should you weight each of the hyperconnections when we combine them into a single hidden state. The post corresponds to this, which is after we go through either the attention or FFN, how do we weight the learnings back out to the hyperconnections? And then the comb corresponds to, like, for each one of these, how much of the previous residual stream should we take in? And so we can see here that for the pre, we do it immediately, where we take the pre and we combine it with x. And then we recast the D type. So at this point, this Y corresponds to this combined. And then we also save the post and the comb. And then so after your attention, you call HC posts with the post and comb that you calculated here. And we can see here that basically we're going to do a bunch of math. And the math is we're going to combine post with x with this weighting. And then we're going to take the comb and the residual, the original residual stream, and do this weighting. And so at the very end, you just have this b by s by 4 by 496 again, which corresponds to this. So yeah, that's hyperconnections. Hopefully that was intuitive. In the next few lectures, we're gonna dive more into attention and SFN. So yeah, see you next one.